agricultural and rural background, but talks about her times at Myrtle Beach, looking at marine organisms and how that created an early love for oceanography and marine biology. She pursued that at the University of North Carolina for both her undergraduate degree, master's degree, PhD in the Department of Marine Science, and has always studied and still studies the kinds of organisms that live in often dark, unusual habitats of high salt, deep in the ocean, performing strange chemical reactions that are unlike many other, or maybe any other environments on the surface of the Earth. So from University of North Carolina, Mandy had a couple of early positions, including one at Texas A&M. That's certainly got to be a hardening experience for anybody in their career. But she escaped from Texas A&M without her long hiking boots, and arrived at the University of Georgia Department of Marine Science, which I've seen her describe at one point as almost a dream job, where she now is the Athletic Association Distinguished Professor of Marine Science. And I love that because it means that somebody at some point made a transition between the athletic endeavors of a university and the arts and sciences. And so Mandy fits that. And she had the good fortune to have established some research projects in the Gulf of Mexico looking at the natural seepage of natural gas and oils from natural fissures in the Gulf of Mexico a number of years ago, and so was in a prime position to study the absolutely unfortunate blowout of the BP Deepwater Horizon oil well, all the techniques and approaches and much perception of how the Gulf functioned already in hand. And she's done that in absolute style, was out on the water shortly after that blowout, has done any number of cruises since then, and has stood up in the face of much hope by many others that something else was true. She has stood up that not all the oil was skimmed off the top or evaporated from the surface or sank to the bottom, but that there was this midwater plume that needed to be explained. What's the fate of that? How far did it get transported? And what will be the ultimate disposition of that material? And she's had to do that. She said standing up for that position based on her data and her work in the Gulf in the face of incredible pressure to cave and do otherwise in the last few years. And so I don't want to say anything more because you've got a great story and I don't want to use a lot of your time, but Samantha Joye, Deepwater Horizon oil spill blowout, scientific inquiry, exploration, discovery, in a rapid response mode. Take it away.
Thanks, Bill. Well, first I want to thank everybody for coming, and I hope to share with you some of the results that we've found in the past 3 years. But I wanted to first talk a little bit about the reason I chose my title. Rapid response science is not something that scientists are taught to do. When you write a proposal to the National Science Foundation or NIH or whoever, you plan things out years in advance, and when you're going to do an experiment, you spend time in the lab and you plan it out and you know exactly what you're going to do. And when you have a research cruise, you have a cruise plan that you plan out 6 months in advance. Every single day, every single minute, every single second, you know what's going to happen. When this oil spill happened, I got a phone call from the National Science Foundation. They told me I had 48 hours to mobilize a team and get to the port and get out on the water because they had a ship waiting for me to go out. And I thought to myself, oh my goodness, how are we going to get together in 48 hours? It usually takes to mobilize for a cruise 6 weeks. We had 48 hours to do that. But we did it, and we got out there, and we have done 16 cruises since March 2010. We had the fortuitous luck to be out there 3 weeks before the blowout, so we have some pre-blowout data. And then we've had 15 cruises since the blowout. I haven't been on every single one of them, but I've been about on half of them. And we've got some interesting stories to tell. And what I'm going to tell you in brief, there are three storylines. One is about the mid-water plumes that Bill mentioned. One is about oil that settled to the seafloor. And the other is about dispersants. And dispersants were sort of the magic bullet, the salvation of the Gulf, because it sped up the degradation of oil. At least that's what everybody was told, and that was the justification that was given for using dispersants. So I'm going to talk a little bit about the reality of the situation with dispersants towards the end of my talk. But first, to sort of set the stage, let me go back 1 second. I have to thank a lot of people. All these people here have been at sea with us and worked with us, and these are long-term collaborators from many, many institutions. And I want to thank all the people in my research group, because every single person has done something to contribute to the work that's been done. Even the people who work on coastal salt marshes. I had several students who work on coastal salt marshes, and they spent time out at sea during this oil spill. So there's not a single person in my group, all 20 of them, have been, out at some point working on the kind of project. So a little bit of context. Global oil consumption. The United States of America consumes 25% of the oil each year that's consumed on this planet. Last year, it was 92 billion barrels, and we consume 25% of that. We produce about 50% of the oil we consume. We import 50% of the oil that we consume. And you can see here, this shows we're the biggest oil hub on the planet. China's next. But this is an interesting figure. It's from Oil and Gas Reports. It's a journal, an industry journal for the oil and gas industry. If you look at the Gulf of Mexico, something else interesting, I want to just talk about why are oil companies going into deeper and deeper and deeper and deeper water. It's because deepwater drilling started, shallow water drilling started in the United States in the 1930s. Okay, so people have been doing this for quite a long time, extracting oil from the seabed. All of these yellow leases here, these are active leases by water depth. Most of these all the oil has been extracted, and they're now extracting gas. Okay? The ones between 1,000 and 1,500 feet are still fairly active. Some of them are producing oil, some of them are producing gas. The ones in really deep water, the green, blue, and teal ones, these are the ones that really haven't been produced yet and have the highest potential. The one that's in the deepest water is the 7,500-foot well that Chevron is now producing. I think it has 2 billion barrels of oil in it. Of course, there were supposedly 2 billion barrels of oil in the Conde Reservoir, too, and that was a little calculation error by a geophysicist by about 3 orders of magnitude. But made their stock go up when they released the SEC filing quite a bit. But anyway, so the reason that we're moving into deep water is we've already extracted all the oil out of the shallow water. And so that sort of sets the stage for my talk. Deep water drilling is a fact, it's happening. Until we wean ourselves off of fossil fuels, it's going to continue to happen, and they're going to go into deeper and deeper water and be braver and braver, or more stupid, however you want to look at it. And they're going to drill in the Arctic. It's inevitable. And if there's a blowout in the Arctic, we're in big trouble, because it's going to take the Coast Guard 10 days to get up there to give any kind of response back. So I'm going to tell you a little bit about the Gulf of Mexico ecosystem. I'm going to talk about natural seepage and how it affects the Gulf system in its natural background state. Then I'm going to talk about the blowout and how it happened. Some of you may know this, but I thought for those of you who don't know exactly what led to this blowout, I would share that with you. And then I'm going to talk about the response and the science and these three topics that I mentioned before: deepwater plumes, sedimented oil, and the impact of dispersants. And these are three things that I've gotten in big trouble for, as Bill said, with NOAA, among other people, because they were things that nobody wanted to talk about. The conversation about this oil spill was quickly turned to, it's all over, the beaches are clean, the oil is gone, the gas is gone, everything is fine. When in fact, the reality was there was lots of oil on the seafloor, we don't know what happened to the gas, and dispersants were not the salvation, and they were a really bad thing. So, natural seepage in the Gulf of Mexico. This is a figure that was provided to me by Ian McDonald, one of my close collaborators that I've been working with for 20 years now. Ian's at Florida State University, and he's mapped out these seep cells in the Gulf of Mexico. There are about 100 of them, and each individual seep cell has a hydrocarbon fingerprint that's distinct. So there's about 100 different kinds of oil in the Gulf of Mexico in terms of flavors. It'd be like vanilla, chocolate, chai, flavors of oil that have a distinct fingerprint. And if you look up here along the slope, this is where they're doing most of the drilling right now. This is where they're going to be doing a lot of the drilling in the next 5 years. These are active sites that you can see oil slicks from satellites. So there's so much oil leaking out of the bottom that you can see it on the surface from the space shuttle. You can see oil slicks. And I'm going to show you a picture of one of those in a minute. But the rate of natural seepage, there's about 1,000 known natural seeps in the Gulf of Mexico, 400 barrels of oil per day. Okay? The Macondo blowout was 50 to 80,000 barrels a day, and we'll never know what the actual number was because it wasn't really properly determined. Natural seepage is slow, as I'll show you in a minute. It's diffused and it's variable. You get natural chemosynthetic communities that go around these seeps, and on the surface you have these little slits that can be centimeters to kilometers in scale. But the shocking fact is that we've done a lot of work on oil and gas dynamics in the Gulf of Mexico, but we never had funding to do it. It was always bootlegged on other projects until the oil spill. So we had rates of methane oxidation, hydrocarbon oxidation, but we had never been funded to do it. We had just sort of done it on the side through other projects, which is interesting. I'm just glad we were able to do it, but the fact that there was absolutely no interest by the government in understanding what happens to this oil and gas is a little surprising in hindsight, given this oil spill. So here is the Deepwater Horizon. This is a picture that I took from a ship in 2006. It was drilling a site near GC 600, a site where we do a lot of work. It's a nice, there are 4 kinds of oil drilling platforms that I've shown down here for you. This is a semi-submersible drilling platform, so it floats. It can detach from the riser here, and here's the blowout preventer on the seafloor. And it's a big monster. It's about the size of a football stadium or thereabouts, college football stadium. And big from each day, that's how I size things by how it's relative to a college football stadium. But this monster was on the surface, and so here it is, not to scale. This is the riser pipe. This is the blowout preventer. And then there was an additional 18,000 feet of pipe going down to the reservoir. All right? So how do you tap? Is this just a straight line? Is this how this looks? Well, no. It looks like this. They start out with a big hole, and then they make it smaller, 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 because there's high pressure down there, and it's going to come shooting out like a rocket. So you want a really small orifice at the bottom of the hole. So once you put in a well like this into an oil reservoir, you put in a plug at the bottom. There are 2 kinds of rigs. There are drilling rigs and there are production rigs. Drilling rigs drill holes. Production rigs pump the oil out of the reservoir. Macondo was a bit of a beast of a reservoir. You can't really see the stratigraphy here. It's not really shown correctly, but all of these layers that are darker color are sand. And one thing that if you're in the oil and gas industry, you know that it's really, really bad to drill in sand because sand is gas rich. And anything that's gas rich is going to cause problems. You're going to have bursts of gas coming back up your hole, and it's really hard to maintain control of the well and pressure in the wellhead. And this well did what's called kick. It would burst methane out about once a day. And sometimes it burst methane out to such an extent that the entire rig shook. The people who worked on this well called it the well from hell. And many of the people who worked on the well were very fearful that they were going to have a blowout because of these constant methane kicks that they were experiencing. So the problem with this well, and the reason that they had a blowout, is that when they were trying to drill this hole, to put this well in, they were running about 60 days over at a cost of about $6 million a day. So they took a little shortcut, and when you're finished drilling in the reservoir, you plug the bottom of the well with cement. And then you put another cement plug up here somewhere, another cement plug up here somewhere, to maintain the reservoir intact. You want the pipe to be, it's filled with drilling mud, you want it to be intact, but you got to get it ready for production. So you cement it up, pump out the drilling mud, and then it's secure, and you leave it and you float away. then the production rig comes, they pop through that little plug, and they produce the oil. So they use an experimental cement that's supposed to set for 72 hours. They let it sit for 24 hours. They started pumping the drilling mud, and the drilling mud is just a counterweight. So you got pressure coming out of the reservoir, and the drilling mud provides a counter pressure to keep the oil from spewing out of the well. So once you got this plug-in, and you've secured and stabilized the well, you can pump the drilling mud out, and it's ready for production. So they started pumping the drilling mud out, and they did a pressure test, and they got a bad pressure test. So they were getting pressure coming up from the well. So they wrote that off as a bad instrument. And they did another pressure test, and they got a negative result, and they wrote that off for some other reason. So then they got a test that was marginal, and they said, okay, we're good to go. We're pumping all the drilling mud out of the well. And when they had about half the drilling mud out of the well blew up. And it was a blowout. And when it blew up, it blew this derrick off the platform, essentially, and the methane spontaneously combusted because it was methane gas that was blowing up through the riser pipe. And then you have this conflagration. And 11 men died, and it's a miracle that more didn't die, and many were severely injured. But this is how it started. And 2 days later, the rig sank, and I want to go back a slide for a second and talk about the blowout preventer. So the first mistake that they made was that they didn't properly seal the well. They rushed it because it would have saved them $6 million. The other mistake they made is that, see this little blow in this figure? You can't really see it well, but there's a blowout preventer here and there's a blowout preventer here. You're required to have 2 blowout preventers. Each one costs $3 million. This well only had one, and it was defective, and it had failed to test about a week before the blowout. And there weren't even batteries in the control panel. So even if it had worked, they couldn't have turned it on because the switch didn't have power. So when the well blew up, the first thing you want to do when you have an out-of-control well is cut your rig off from the source of fuel, right? So you either have to cut it off by the blowout preventer engaging, which is essentially a big metal shear that cuts the pipe, okay, and releases the riser. Then there's a second sort of blowout preventer. It's not really a blowout preventer. They call it a emergency shear release. And it's supposed to cut this pipe right here. So it cuts the platform free of the riser, and then the platform floats away, and the fire is localized at the source. This didn't work either. So that's why the fire was, there was no way to extinguish this fire because there was no way to control. The only way that this fire could have been extinguished on the platform was to get the platform away from the fuel source. And then there would have just been a huge fire in the ocean, but if the platform probably would have survived. So I want to go back 1 second, and before I show you this video, I'm just going to stop it. I want you to see the contrast between natural seepage and the Deepwater Horizon blowout. So this is the natural seep. And if you digitize this image and count the number of oil bubbles, this is about a foot across here. And count the number of oil bubbles that are coming out, it's about 15 bubbles per second. And you can size the bubbles and figure out how much oil is coming out. It's a very tedious and boring job, as some graduate students have to do tedious and boring jobs. But it turns out that this particular little fault fissure right here releases about 1/10 of a barrel of oil per day, which is pretty minimal, but it's enough to make a oil slick on the surface. So I'm going to go out of here for a second and go down here and pull up and show you the Macondo wellhead. This is some footage that I got from a friend of mine at BP, and I'll leave it at that. But this is what the wellhead looked like. It was literally a fire hose, and the dark part of the fluid, I'll play that one more time for you. The dark part of the fluid is oil rich, and the yellow part of the fluid is gas rich. And I don't know why that is, but that's what they determined when they analyzed the fluid. But you can see, and this is after they cut the riser pipe. So this was taken in June. So there were some really weird and interesting things about this oil well, about this oil spill, that I was sort of fascinated by. one was, what's going to happen to, where's the oil going to go, and how are the microbes going to respond to it? And that's what I'm going to talk to you about today. But I promised to show you a satellite image of the oil. This is taken from the RadarSat satellite that rotates around the Earth. It's a NOAA satellite, and it takes pictures. Essentially, it bounces radar off and takes images. So the light-dark contrast, this is all surface oil from the blowout. And what's really cool in this picture is that you can see my favorite seep in the Gulf of Mexico, the one that I just showed you the video of, is right there. And these little wisps are natural seeps, and this is the blowout. Huge area impacted by this blowout. And if you look at model results and model outputs, some of the oil went over to Florida, but most of it sort of stayed, within this 10,000 square mile area, or thereabout. But there's some interesting things. This is a NOAA picture of a plane flying dispersants that are the oil spill. I'll talk about dispersants later. And the other thing they did that was really unprecedented was fires. They burned 742 fires to try to burn off the surface oil because they were having a real hard time skimming it. And that had repercussions too. But the scale here is 200 kilometers. I forgot to point that out before. So this was a huge area that was impacted by this spill on the surface. And then there was this whole issue of what was going on under the surface. So when we got out there to the site, it was an amazing thing to see because you're out in the middle of nowhere and there's a city of ships. There were more ships than I've ever seen anywhere, and they were all just, so these are the two relief well drilling rigs, and this is the ship where they were doing the ROV operations trying to seal the well and close it off. This is the Global Explorer, the DD2, and the DD3, and these are all the red ones are the fire ships, the ships that were spraying water everywhere to make sure there were no fires, because there were high concentrations of volatiles in the air. So there was this big thing of who studies what, where, and when, and how do you give money, and how do you go about it, and whatever. So we had a cruise scheduled, and we just retasked the cruise and went out there, and then we got back, and had been back for a couple of days when I got this phone call from Minnesota going, we're having another boat. Can you go back out in 2 more days? And we were like, okay, we just wrapped out, but I guess we can. And we went out again, and then we went out again in July, and we went out again in September and August, and we went out again, and then we were in December, and then we've been out multiple times since then. But independent scientists were really the first ones on site asking pertinent questions. And I think that's really, well, it's interesting and it's disturbing because we have no national oil spill response plan. We didn't have one when Exxon Valdez happened. We didn't have one when the Deepwater Horizon happened, and we don't have one today. And that's an interesting point that, we just sort of pretend that it's not going to happen again. Okay, it happened that time, but it's not going to happen again. It's going to happen again, and we need a national oil spill response plan, so we don't have it. So the scientists like me, went out there, and we started asking some questions that we thought were interesting. What's happening to the oil and gas? Where's it all going? Somebody needs to document what's happening to it. How much is coming out of the well? That's an interesting story that I'll tell afterward if anyone's interested in knowing how that number came about, because BP didn't want anybody to know how much was coming out for obvious reasons. What are the impacts on the ecosystem, from top to bottom? Not the coastal system, but the pelagic system. And what background do we compare this against? This is a huge problem, and this is being used, this is an incredible debate that's going on in court in the case, because BP is saying, well, prove that there was damage to the ecosystem. And how do you prove it if you don't have background data? Well, we have background data, but not many people do. And it's just it's a big problem when there's the oil industry, in my opinion, should be forced to have a monitoring network so that there's background data. And they need to do that in the Arctic, and they need to start right now, and they need to be doing anywhere that there's deepwater drilling going on, because there's going to be a problem at some point, and we need to know the background so we can see how much damage was done. So, Developing questions in a disaster scenario, or any scenario, requires pertinent knowledge. You gotta have background knowledge of the system. And one of the things that I knew in my gut from day one was gonna happen as a result of this oil spill was that there was gonna be a lot of oil and gas underwater that nobody could see. And the reason that I knew that is because there were 14 publications between 2000 and 2005 talking about formation of deepwater plumes when you had a deepwater blowout. And in fact, the Minerals Management Service, which was renamed BOEM, the Bureau of Ocean Energy Management, after the oil spill happened, funded this project called Project Deep Spill. It was a collaboration with the Norwegians, and there were 15 oil companies involved in this project, including British Petroleum. And what they found in there, so what they did was they simulated a deep sea oil spill in the North Sea. And what they found was that, wow, there was a deepwater plume, and it was enriched in hydrocarbons. And it extended for quite a distance from the source of the oil input. So, and there have been published papers, and there have been models. So everybody should have known that there was going to be a deepwater plume, yet nobody was looking for a deepwater plume. So the first thing we did was look for a deepwater plume because we knew, well, we had good reason to believe that there would be one. And it turns out that there was one. In fact, there were many. Because what happens when you take oil and you shoot it out of a fire hose, the temperature of the reservoir was 128 degrees. The temperature of the bottom water at that site was 4 degrees. So you weren't on, and it was high pressure, 18,000 feet to, 5,000 feet. So huge pressure gradient, huge temperature gradient, and you're shooting it out of a fire hose at the bottom of the ocean. What you're going to do is essentially aerosolize and make little tiny particles of oil that float in water. But they don't float to the surface, they're actually neutrally buoyant in water. And what you see here are neutrally buoyant layers of oil that formed in the Gulf of Mexico. So these are what the deepwater plumes look like. And if you were to go into anywhere in the Atlantic Ocean or the Pacific Ocean or the Gulf of Mexico, whether there hadn't been an oil spill, you'd see some squiggliness in the lines in the upper 100 meters, because that's where all the biology is happening. But the lines are flat and boring in the bottom. There's no structure like this. I mean, nobody had ever seen anything like this in the deep water. And people thought we were crazy when we first showed these photos. Like, how? No, you must have had screwy instruments. You got oil on your sensor and it was foul. But we have probably 400 casts, or maybe, I think it's actually more like 650 casts, where we see these layers. And in here you see the red line is essentially the oil signature. The purple line is beam attenuation. That's like bacterial abundance, particles in the water. And then the green line is dissolved oxygen. And what you see is where there's oil in the water, there's oxygen drawdown. So there's microbial metabolism of that oil in the plume. So there's a lot of oil in the plume. This is the levels that we measure, up to 1 milligram per liter. That may not sound like a lot, but that's a lot. And it wasn't like you could see it. It was actually invisible. You could filter a liter of water onto a filter, and you could see the oil. But when you looked at the bottle, it looked clear. It was really kind of amazing, because they're microparticles, and they're not visible to your eye. But you can shine a black light on it, and you can see all of these little black dots, green dots of oil in the water. So this is what the background looks like in the Gulf of Mexico, and this is what was in these plumes. So huge, huge elevations of oil by up to 100 times to 1,000 times in concentration. And for methane and gases, it was even more extensive. Background methane concentrations in the Gulf of Mexico deepwater are about 10 nanomoles per liter. So this is about a 75,000-fold enrichment in methane in these plumes. So these plumes were enriched in oil, they were enriched in gas, and they had lots of microbial activity going on. So the microbes were eating the oil and gas until they ran out of nitrogen, because nitrogen is the most important element, and it limits production of microorganisms in the Gulf of Mexico and other places. So this is a slide that most of you are going to go, God, what in the world is that? but I want to show it for there's a specific reason I want to show it, and you don't have to pay any attention to this. All you have to pay attention to are the top. So this is pre-spill. This is microbial community composition with a really fancy technique called high throughput sequencing, where you can essentially tag the microbial community and then identify who's out there. And what I want you to notice is that this is the community before the spill. So the brown guys, the purple guys, and the green guys dominated. And this is our control site that was 200 miles away from any place that had oil. And it looks like a natural community, right? But what happened in the core of this plume was you had this explosion of the green guys. And the green guys are gamma proteobacteria. And the gamma proteobacteria are the bugs that eat oil and that love oil. So these guys bloomed and exploded in the core of the plume where that big sharp line was. And above the plume, you got some explosion of the green guys and these purple guys like cyclobutane and cycloalkanes and aromatic type compounds. But below the plume, the oil was moving up, not down at this time. The community looks more like a control community, but you still had some of the green guys coming in. So the gammas were down there too. So there was a little bit of oil that was in the deep water, but there was a lot of oil in the middle that's selected for a very different microbial community. And then this is sort of after the spill. And what I want to draw your attention to is the fact that after the spill does not look like before the spill. The community, the system was perturbed. It was sent into a chaotic state, and it settled back down at a different state. So it started down here, it went crazy, and then it came down and stopped here. So the community that now dominates the water column of the Gulf of Mexico is different in terms of the microbiology than it was before the oil spill. So to say there are no long-term consequences is a bit of a, well, you can't say that because the microbial community changed, and what we're trying to figure out is did the function of the microbial community change? And it looks like a lot of the processes that these organisms mediate have actually changed since before the oil spill. So now we're going to move into part 2 of the story, and that is what happened to the surface soil. And this is one of my favorite plots ever. This is the NOAA oil budget. It's a pie chart that was generated with no data. And I'm not being facetious, I'm serious. It's a pie chart that was generated with no actual data. They did sort of know what the flow rate was. They noticed this possible alternative estimates, okay? And look at the variability in the pie chart, okay? But this was actually presented at a press conference, and I forget the woman who gave that press conference, but she was summarily dismissed and never heard of again after the press conference, because this did not go over well with the scientific community, because there was no data to back up any of these numbers. And let me just walk you through it to tell you why, to explain why it's a problem. So, direct recovery from the wellhead was estimated to be 17%. Well, first of all, you can't even make percentages unless you know how much oil was released, right? You can't say what happened to anything unless you know how much was released. And they didn't at this point know how much oil was released. So these are all sort of relative, fancy land type numbers. But so 17% was recovered from the wellhead, 5% was supposedly burned from the surface, 3% was supposedly skimmed from the surface, 8% was supposedly dispersed at the surface or at the wellhead. So they think that they applied dispersant to 8% of the oil that came out. 16% was naturally dispersed, mainly at the wellhead. The deepwater plume was not formed by dispersants. It was formed by the fire hose effect, and essentially the aerosolization of the particle, making these really fine particles as the oil jetted out of the pipe. So not dispersants. It was natural. 25% evaporated to the atmosphere. This number is based on a sample of oil from the Gulf of Mexico that was put in a wind tunnel at NASA Ames in California, and they shot some jet engine over it, and they measured that 25% evaporated after this jet engine blew over it for 70 hours. And they applied that number to get that 25% evaporated. So this is an imaginary number. And then this is the residual remaining oil, 26%. So what they tried to do with this pie chart is say that essentially 74% of the oil was gone and only 26% remained. When actually, this stuff, they don't know what happened to it. It was still there. This stuff is a fantasy number, and this stuff is definitely still there. So the reality was that this stuff was probably gone for sure. So 20-some-odd%, let's give them 25%, is gone. And the other 75%, they don't know what the heck happened to it. And they don't know where it is. So we were kind of curious to figure out what happened to all the oil. And, the measurements that we made of microbial degradation in the deepwater plumes suggested that the microbes became nitrogen limited and they weren't able to consume all the oil. So what happened to the oil? So this is a figure that was published by Terry Hazen and Ron Atlas, and they estimated that, this cloud of oil droplets, nobody liked the idea. This plume word was a bad thing for some reason. So all the people who were part of the natural resources damage assessment called this an oil cloud. I think plume is just kind of a description, this oil cloud. But here's our oil cloud, and then some of the oil went up to the surface. They said 25% was down here, 75% was up here. Again, imaginary numbers. We'll never know because it wasn't properly measured. But this is what it looked like on the surface, and this is what it looked like coming out of the riser pipe. Again, this is a picture that I got from somebody that I know at BP. A lot of this oil, I'm going to argue, ended up on the seafloor. And we've got some pretty good radiocarbon data. Oil doesn't have any radiocarbon in it, so you can use radiocarbon as a tracer of oil, because if you get areas where there's no radiocarbon, then it tells you it's been petroleum deposition. And from our numbers, we can say that anywhere from 5% to 35% of the oil that was on the surface ended up on the seafloor and still sitting down there on the seafloor. So this is a map of the surface distribution of oil, and it's a frequency map. And in this little hexagon here in the middle was our where we focused our work on oil on the seafloor. And this was the area where most of the time, about 80% of the time, this area had oil cover on the surface during the discharge. So this was an area that had an oil sheen, oil tar mats, etc., covering it all the time. So we went out there. Here's the map it's a little bit of a different shape, but this is a map of the area that we studied. These are all the sites that we sampled, and we sampled these sites now, I think, 14 times. This is me standing on the multiple core. This is the instrument that we use to sample the sediment. You drop it off the side of the ship. It collects 8 beautiful cores. You bring it back up, and you pull your cores off, and you sample them. And you have to wear a hard hat because sometimes it bangs you in the head and gives you a very bad headache. I've had that happen. It gets rough out there, and this thing's really heavy, and getting it on the boat in rough weather is difficult, but it is possible. This is the wellhead right here, and we did a lot of work down the south channel, and I'll show you in a little bit. NOAA didn't look at all down here. This wellhead is sitting on the side of the hill. It's hard to tell. And you'll notice all the topography here. These are all salt bones that are pushing up. So these are like little underwater mountains and then underwater valleys. And the plume flowed right through here to the southwest. And a lot of the oil was deposited up here to the northeast. So what does this stuff look like? This is oil that's been chemically dispersed. It's red because they put iron in the correct. So it's red colored, rust colored like iron. And these are microbial slime strings. These microbial slime strings are a very normal, natural, biological product of the microbial degradation of oil. Microbes can eat oil, and they're really good at it. And these emulsifying agents that they use are much better than Corexit, as you'll see in a few minutes. But this is a layer. This is a sediment core that was deposited by natural oil slime sedimentation. And this is the sediment core. You can see it's redder. It came from dispersant deposition. There's no microbial activity in this layer, and there's not much in this layer, but there's more here than there is in here. Because the dispersants, again, are a good thing. But so how do we know that this isn't just some natural seep, that we're not sampling some natural seep? Well, this is a natural seep. It's black. It has oil floating on the top of the core. It smells to high heaven. And the chemistry of a natural seep sediment is pretty distinct. It has high concentrations of the metabolic breakdown products of hydrocarbon degradation. So the microbes eat the oil, and they make all these products, and you can measure them. And these are some of the things that we measure. And this is very different from what we saw during the oil spill. So here's a control core from off-site, very boring, very brown, no black, no oil, no smell, it's boring. This is a site from a natural hydrocarbon seep. If you shine a black light on it, the oil fluoresces purple. You can see that here. And this is a site with one of these weird layers. You'll notice that a natural oil seep, you don't get that layer, right? You only get that layer when you go into these Macondo areas. And we didn't sample one site that didn't have this layer. Every single site that we sampled had this layer. And this layer is fresh. We can use naturally occurring radioisotopes to date it, to say when it hit the bottom. And it hit the bottom between July and November of 2010. So it's a very young, freshly deposited layer. And this is what the same site looked like in May. So the layer's not there in May, and the layer's there in September. So lots of deposition happening over a short period of time. So how did it get to the bottom? So we did some experiments in the lab with some colleagues at UNC. We added oil to bottles. We put them on roller tables. We incubated them, and lo and behold, they made these slime stringers, and you can see the little oil droplets emulsified into this slime. And this stuff is so sticky, it's like flypaper. Everything sticks to it. Phytoplankton, clay particles, debris, everything. And it gets heavy, and it sinks to the bottom of the bottle after about 21 days. So this is one mechanism of getting oil from the top to the bottom, is natural microbial processes. We went out there and we took sediment traps, which are these little particle interception traps. We deployed them at 4 places around the wellhead and 4 places way to the south, about 200 miles to the south of the wellhead. And what we saw was down south, there was very little sedimentation, but around the wellhead, there was lots of sedimentation happening, lots. And if you look at the relative rates, something that's really interesting is that it's all organic matter that's being deposited. It's not inorganic material. It's 94 or 95% organic. So this is a really sort of the smoking gun for the rapid sedimentation from the top to the bottom. So a lot of this oil came down and it blanketed the seafloor. This is another picture to show you. These are cores from several sites. This was a sort of a control site, but all these sites have this oily layer to varying degrees. Sometimes it was a centimeter thick, sometimes it was 5 centimeters thick, sometimes it was 5 inches thick, depending on how far or how close you were to the wellhead. The other thing that sent a lot of oil to the bottom was the burning that they did. And I don't know how much it was in the news, but it was the most bizarre thing to be out on the water at night and look around because it looked like the ocean was on fire. There were just fires burning everywhere. And if you count the fires, the individual fires in this image, there are 19 of them in just this one image. And these things this picture was taken from 2 miles away, and you can see the flames reaching up off the water. So they would boom the oil into they would corral it, and then they would throw a Molotov cocktail in and set it on fire and blow it and burn it up. It was crazy. So when you so this cloud of pyrogenic PAH poison, the airshed of this stuff is Georgia. And I gave this talk to the Georgia Senate and Congress, and there was this audible gasp when I asked this, and so where do you think all this stuff ends up? And they're like, well, and a little bit of South Carolina, and then it goes out into the Atlantic. And, you know, somebody asked me, well, is anybody measuring air quality and deposition of, you know, chirogenic PAHs, which are very carcinogenic? And there were absolutely no measurements made of that sort of stuff. But there was a lot of combustion product made. And you don't just make smoke when you make fire, you also make soot, right? And all that soot and char settle to the seafloor as well. And we can measure it in the sediments. We can see soot and char in the sediments, which is kind of weird. But again, it's just another pathway to get stuff from the top to the bottom. This is some data from some of those cores that I just showed you. And this is thorium. This is this natural isotope that I was talking about. But the natural level of thorium is 6 disintegrations per minute per centimeter squared. This little bar here is 40 disintegrations per minute per centimeter squared. And what you can see is that there's not a site around this area that has natural sedimentation. This sedimentation pulse was broadly distributed throughout this entire area. So there was excess thorium everywhere. And the only way you can do that is to rapidly burn stuff from the top to the bottom. This is hydrocarbons. And again, total petroleum hydrocarbons and PAHs. The background PAH levels in the Gulf are about 0.02. So and this is 2 micrograms per gram. And total PAH background is 1 microgram per gram. So you can see that we're way elevated over background. So again, these areas of rapid sedimentation had elevated concentrations of hydrocarbons. So the oil was going from the top to the bottom. And this is something that surprised a lot of people, but it did surprise me because I thought, you know, where is it going to go? It's going to sink. You know, it's going to get degraded and it's going to sink, and the dispersants are only going to amplify that. And that's the third way that you get oil to the bottom, is dispersants. This is a patch of dispersed oil, and it forms these tar mats. So I'm going to explain to you in a minute how dispersants work, for those of you who don't know. But the question is, are they good or bad? Are they useful or are they useless? Because really, prior to this oil spill, there was no definitive data showing that dispersants had any positive effect whatsoever. The only thing that they were known to do well was sink oil, okay? But they were sold to us in this particular oil spill as a way to make the hydrocarbons more available and help the microbes eat the oil. The question is, did they really do that? So here's how they work. So here's a plane, spraying corrects it. And these surfactant molecules have a hydrophobic group and a tail, and they form these micelles around the oil, and they break the oil up into little pieces. So you go from having an oil slick to this layer of thick oil on the top, but if you go down into the water column, you've got all this dispersed oil that's in the water. It looks like chocolate milk is what it looks like. When you look at it, if you go in the lab and you add some dispersant to oil, it instantly turns into this chocolate milk foamy looking thing. So the dispersants take the oil from just being on the surface and they push it deeper in the water column, and then it forms these mats that are heavy and it sinks to the bottom. But the question is, do they really help biodegradation? Do they really do anything positive in terms of oil remediation? Or do they just sink the oil and get it off the surface so that we can say there's no oil on the surface, so we no longer have a problem? So we did an experiment in the lab, so we being one of my postdocs and 3 graduate students, where we produced this water-accommodated fraction, which just means we took oil and we let the oil dissolve into the water, and then we took the dissolved oil. So we didn't just add oil to bottles. We simulated the plume. We added this dissolved oil to the bottles, which is really, really important because nobody else does that, and I think it really alters your results. But I can tell you more about that if you're interested. We amended our treatments with the same amount of carbon. So we had a treatment that was abiotic, so it was sterilized. So there was no biology. We had a biological control that didn't get any oil or any dispersant. And then we had one that we added dispersants to, one that we added oil to, one that we added dispersed oil to, so oil plus dispersants. And then we had another treatment that I threw in for kits, oil, dispersants plus nitrogen. And this This was a monster experiment. These are 2-liter bottles on this big giant roller table that, I don't know, it's huge. It weighs like a ton. It takes 4 people to move it. But it can hold 100 bottles, 100 of these 2-liter bottles, and it rolls the bottles to simulate sort of the motion in the ocean. Because the ocean's not static. The ocean is a place where there's always motion. So we sampled these bottles about every week for 6 weeks. Because that was about as long as we could. Well, we only had enough space on the roller table to do a 6-week experiment. We wish we could have done 12, but we would have had to buy another roller table, and we didn't have anywhere to put it because our environmental room barely held this one. So we sampled these things in triplicate at all these time points. I'm going to show you some of the data because it's really interesting. Here's another one of these crazy molecular biology plots. But I want to note a couple of things, and I think it's kind of cool for a whole variety of reasons. Here's our water when we first collected it. Here it is when we ran an experiment 2 weeks later. So the community changes really fast when you put it in a bottle, and that's not a big surprise. But we know our starting point, okay? And that's the important thing. We know what the community was when we started, and we know what the so-called bottle effect was. So if the microbes changed just because they were in a bottle, we get that from this treatment right here. And you can see that there was some change in these little orange guys. These are flavobacteria. Flavobacteria like to eat. They'll eat anything. They're like that kid in the commercial, my kid will eat anything. These are the flavobacteria. They eat anything. If it's juicy and yummy, they eat it. And they grew in this experiment. They also grew in the dispersant treatments. And some of my little stars aren't showing up, but I want to highlight a couple of things. First of all are these little teal-colored bars right here in the dispersant-only treatment. So this is dispersant without oil. These organisms right here are called Colwellia. They're gamma proteobacteria, and they were the dominant organism that people saw in the Gulf of Mexico after the oil spill. And everybody said, oh, the oil-eating Colwellia are saving the day. But were they eating oil, or were they eating dispersants? I think they were eating dispersants. Because we see them in the dispersion-only treatment, and we see them in the dispersion plus oil treatment. But what's really, really interesting is these little green guys here. These are called Marinobacter. Marinobacter are known oil degraders. They are the dominant organism that we saw in the surface oil slicks that didn't have dispersants in them. If they had dispersants in them, there were no Marinobacter. But what this data shows us is that dispersants change microbial communities. They cause them to evolve. And they change them in such a way that you get domination by this, Colwellia, and this is Cycloplasticus. But wow, the Marinobacter aren't in either of these treatments, in the dispersal treatments. And these are the guys that are really good at degrading the oil. And in the nutrient treatment, we got a totally different reaction. We saw some Colwellia, and we saw some Marinobacter, but not nearly as many Marinobacter as we saw in the oil-only treatment. So the dispersant treatments grew Colwellia, the oil-only treatments grew Marinobacter, and selection of one group over the other could have really important consequences for oil degradation rates if the Colwellia aren't eating oil, if they're eating the dispersants instead of eating the oil. And that could really alter the hydrocarbon degradation efficiency. So does it? I'm only going to show you a couple more slides. This is hexadecane oxidation rates, okay? Guess which treatment has oil only? Don't look at the bottom. The red one is the oil only treatment, and this is the dispersant treatments. Dispersants inhibited oxidation of alkanes. Alkanes are the easiest hydrocarbons to eat. They're like the chocolate of the hydrocarbon family. And dispersants completely nuked the alkene degradation. Completely. What about polycyclic aromatic hydrocarbons like naphthalene? Well, dispersants stimulated naphthalene oxidation in the very beginning of the experiment at time 0 when we instantly added it to the water. So before the community had changed, when the natural community was there. But by the time the Colwellia had come in, there was absolutely no difference between the oil and dispersant treatments. So dispersants had absolutely no effect, no stimulatory effect on PAH degradation. PAH is the most toxic component of oil after benzene and toluene and ethylbenzene. And dispersants are supposed to stimulate hydrocarbon degradation. So what we see is either inhibition or absolutely no effect of the dispersants on degradation. So what conclusions can I come to from all of these data? Well, the first thing is that I cannot collect iCloud. My computer is obsessed with iCloud, and I don't know why, because I don't use it, because it's kind of scary. I've had files disappear from iCloud, but it wants to collect with connect to iCloud all the time. But these deepwater plumes, getting back to the real world, are a natural consequence of a deepwater blowout. We need to know more about them. We need to know what the microbial communities do in these plumes. We need to track them over time. We try to get money from NSF and NOAA to really track these plumes, to put drifters in the plumes so that we can know exactly where they were going, because otherwise you're looking for a needle in a haystack. You know, we got so lucky when we found these plumes, and it was only because we had previous data and we knew where the deep water currents were floating. So our guess was that it was going to the southwest, and we guessed right. Otherwise, we would have had no idea where to look. So if we hadn't had that preliminary data, we would never have known where to look for these plumes. But they're natural. They weren't formed by dispersants, and you can't prevent them from happening in a deep water blowout scenario. So some fraction of the oil and all the gas are going to end up in these deep water plumes, and we really don't understand how they work. The oil-degrading ecotypes, that the bugs that eat oil, that were abundant before the blowout, were not the same ones that were dominant after the blowout. I showed you that first figure of the community shift, where you had this one community, then this bloom of the gammas, and then boom, a different community. So what does that do to the functioning of carbon and nitrogen and phosphorus in the system? We don't know. That's one of the things that we're studying in our long-term project. We know that a significant fraction, up to 30%, of the released oil settled to the seafloor with negative consequences for benthic fauna. Now, I didn't talk about this, well, you have to trust me, that when you dump all that oil on the seafloor, anything that can't run away and move is going to get suffocated. They're going to suffocate. Corals, invertebrates, any fauna on the bottom that couldn't get out of the way or swim out of the way was essentially killed by this. And we're talking about thousands of square miles of seafloor where this happened. Dispersants drive community compositional changes in this simulated deepwater plume experiment. We showed that very nicely. And the interesting thing that I want to make sure that I mention is that if you look at the community evolution in our dispersant treatments, it's the exact same thing that people saw out in the field. So one wonders whether those Wellhead and Cycloplasticus were eating oil, or maybe they were just eating dispersants. I think they were probably eating dispersants. The thing about it is that the dispersants, I forgot to mention, we used correct 9500, and who came up with this name? It doesn't correct anything. It makes it worse. It didn't stimulate hydrocarbon degradation. Activity was either inhibited or unaltered, and the total oil degradation rates were actually much lower in the dispersant treatments. We measured oil concentration and composition, and we know that there's way more oil. About 70% of the oil was spilled in the bottles in the dispersant treatments, while only 22% of the oil was left in the oil-only treatments. So those guys went to town on that oil when it was just oil. But when you add dispersants, they don't eat the oil. They eat the dispersant instead. So that leads to my final conclusion, in that there is no good justification for applying chemical dispersants as an oil spill response action. They do not stimulate biodegradation of oil, but they do a very good job of sinking it. And the question then becomes, is this a good response action? Because there are a lot of other potential negative consequences of dispersants in terms of biological consequences and problems with corals and fish and shrimp and all kinds of organisms that I don't have time to talk about. But right now, the oil industry, dispersants is their first line of defense. Every platform is now equipped with a dispersant applicator, both at the surface and at the seafloor. And if they have a spill, the first thing they're going to do is start spewing whatever kind of corrects that they have in their inventory into the water. And I think that's a real problem. And I'm hoping that this paper that we have submitted will change the story a little bit in terms of dispersants, because nobody's really done the experiment that we did, where they measured community composition, hydrocarbon oxidation rates, total hydrocarbon pools. We even measured the dispersants and the dispersant breakdown products. So we can show that the bugs were eating the dispersants. Okay, it disappeared. It got eaten and turned into microbial biomass. So with that, I'm going to leave you with some pictures, and I'm happy to answer any questions that you might have.
You had mentioned earlier in your talk that before drilling is done, say for example in the Arctic, there should be a pre-inventory. That wasn't your term, but a pre-inventory. Could you tell me what you would like to see in that pre-inventory?
Yeah, I would like to see essentially measures of microbial populations. I'd like to see some studies looking at oil degradation rates. And I'm actually, to be upfront, I'm talking with Shell, because Shell's got the first well that's going to be drilled. And I'm trying to work out a deal with them where they provide me with oil from their reservoir, sediments from around their well, and water from around their platform, so that we can do experiments where we dose the water in the sediments with oil to see how the community responds. And in the Gulf of Mexico, in the deepwater plume, it was 80 degrees, and the surface was 32 degrees. You know, the guys on the surface were going to town until they ran out of nitrogen. The Arctic is not 32 degrees, ever. You know, it's 9 degrees in the summer, and it's going to be a big temperature regulation of biochemical processes is a well-documented phenomenon. The Arctic is an oligotrophic ocean. There are no nutrients there. So what's going to constrain the microbial ability to degrade this oil? That's what I want to know. And hopefully we can work out a deal with Shell to make this happen, because for them, it's good PR, and they know that they need to know because of this. They know they need to know.
Jerry?
Two questions. One, do you have enough data now to review the NOAA budget so you know where they're going to went?
The question was, do we have enough data to redo the NOAA budget to estimate where the oil went? I think we do. And in this paper that I'm about to submit, we do that. And we do it based on radiocarbon, for the most part. And we do it based on we made some respiration rate measurements and degradation rate measurements in the deepwater plume and in the surface oil. And essentially, what didn't settle out, a lot of it, what wasn't on that oil budget at all, if you noticed, was beaches. Like, there was no part of the pie for how much of the oil came around, how much of it hit the shore. And that, I think, was around 20%. If you just sort of look at the distribution of what was oiled and how thick the oil was and whatnot. So that 20% of it came around, about 30% of it ended up on the seafloor. We've already said that, 25% of it we'll give them for recovering it. So that leaves another quarter that we need to account for. And I think that stuff either got metabolized in the water column. That's the wiggle number that we don't have good constraint on, is how much got metabolized in the water column. And 25% is a number I'm comfortable with. Because what I did was I took the amount of oil I took a high and low end of oil that was in that deepwater plume and some on the surface, and I calculated how much nitrogen was in this volume of water that the oil was injected into. And I used nitrogen because there's the N to P ratio. I figured nitrogen is going to limit it. You could do it with phosphorus too, and you probably come up with the same number. And what I come up with when I do that calculation is that the biology could only consume between 20 to 30% of the oil before they ran out of nutrients. So I think that 25% is probably a realistic estimate. And so there's all accounted for.
Way in the back there.
I have a question about the events immediately prior to the catastrophe itself, and perhaps you and other independent scientists can offer some insight to the public about it. And that has to do with the fact that prior to the explosion, President Obama's Secretary of the Interior, Ken Salazar, appointed a senior executive from British Petroleum to be the director of, the deputy director of lands and mineral management. And then we have the explosion. I mean, does anyone know what happened to her? Was she given a golden parachute or an
She
award
was
of
sort of
service?
parachuted out very quickly. Her name never came up. She was never had anything to do with the oil spill. So I think I don't know if she was parachuted out or transferred to another division or given a different title, but she was certainly not involved at all. And it's interesting, you know, when Exxon Valdez happened, they essentially said, Exxon, you're the responsible party, and you will fix the mess you have created, and we're going to stand over here and watch while you fix it. And that didn't work out very well for anybody. So when this happened, when the Deepwater Horizon exploded and blew out, there was more of a, and I think this was a big mistake, my own personal opinion, but there was more, remember the joint news conferences between the BP guy and the Coast Guard person? And that just did not go over well, because it looked like, you know, well, who was in charge and who was responsible, and and that went on for about a month, and then it was just the BP guy in the news conferences, because they realized that it was causing a mess. But the responsible, under the Oil Pollution Act, the responsible party is the driller, and the driller is responsible for cleaning up, and the U.S. Coast Guard is responsible for holding the responsible party accountable for cleaning up the mess that they created. Now, the economy was in the tank when this well blew out, and I think if I learned a lot of things about science, but I learned a lot of things about politics too. There was enormous pressure for this just to go away, because it was a problem that it was a problem, and they wanted it to go away, and it went away because the whole budget was published and it went away. It was August the 8th, 2010. There was a news conference, and the oil is gone. The Gulf is safe. Eat the seafood. Swim on the beach here. Blah blah blah. It's fairyland. It's fine. It's all gone. And as a hydrocarbon microbiologist, you just scratch your head and it's astounding. And the thing is that people that didn't live on the Gulf Coast had no reason to disbelieve it, right? I mean, but if you live on the Gulf Coast or you work in the Gulf of Mexico, it was just phenomenal. And I remember when we went out there on our coring cruise in August and September of 2010, and we first did this southern transect, you know, way below the area of Macondo impact, because we wanted to get background cores that were uncontaminated, because I knew there was going to be oil all over the place on the seafloor. And when we found that first core of oil on the seafloor, I had a cruise blog, and I don't remember when I called the blog, but it was like, open your eyes and you will see, you know, or it's like, don't be blind, open your eyes and look and you'll see. You'll, you know, what you think is there, it's right there, it's in front of your eyes. And I got a phone call, it was within an hour of the blog posting going, that's not oil, you have no evidence that it's oil. And I was like, look, we have a VOC analyzer on the ship, and the benzene levels in the water above this core are through the roof. This is oil. And I wouldn't put a blog posting saying that it was oil if I didn't have evidence that it was oil. It's stuff to high heaven. Of course it was oil. I mean, what else is it going to be? But this person was just like, you can't say that. You can't say that. You just can't. You have to run it in the lab and analyze. And I'm like, we have a lab on the boat. We're scientists. We have instruments. We measured the benzene. It's in the water. There's oil on the seafloor. And this person just did not want to hear it, so I hung up on him. And the next day, I got a call from Richard Harris at at National Public Radio, and he had been following my blog, and he was like, wow, this is really cool. Can we call you, because we want to do a story on this. So they did this story on oil on the seafloor, and that's when NOAA finally admitted that there was oil on the seafloor, and they started looking for it. They weren't even looking for it before then. So they started a program, and the funny thing is that they got all the sites where I went to. I gave them my maps, and I said, here's where we sampled. And they went out and they sampled at the same places, and they're like, we're going to prove that she's full of it. And they found the exact same thing that we did. But when they published their report, they give the levels. There was only this much pH. They don't tell you what was supposed to be there naturally. There was only this much PAH, and there was only this much total petroleum, and there was only this much. So it makes it sound like there's nothing there. And the layers were minimal. Instead of, 5 centimeters is not minimal to me, but it could be minimal to someone else. So it's really, it's interesting how this was sort of played out in the press. And the oil on the seafloor, I got in way more trouble for that than I did for the Deepwater Plumes. That was and it was a bit of a, I don't know, I didn't know much about dealing with reporters before this thing started. And obviously I like to talk. And when reporters would ask me questions, I would give them, soliloquies, long ones sometimes. And this one guy from Dan Rather Reports, Lynn Rayburn, he came on board after we found the oil on the seafloor because they wanted to do a piece on it. And they were doing the video interview, and the interview was over, and I had the mic in my hand, and the camera guy wasn't beside the camera, so I didn't think he was rolling. I didn't think that he was still filming. And he asked me this question. He said, so how much oil was on the seafloor? Was it this much, or this much, or this much? He said, can you give me I was like, well, it varied. And he says, well, what was the deepest, how much oil in the worst spot did you say? I said, well, the deepest spot, it was like that much. 5 inches, something like that. And so that's how they started this story, was that there was 5 inches of oil sludge on the seafloor, which is not what I said. I never said oil sludge, and it was completely, I thought, he asked me this off-the-record question, and I got in so much trouble for that. And I made him do a retraction on the next show to clarify what I had. Not that he would pay attention to that part of it. He never pays attention to the retraction, but they did actually do it, because I was really annoyed. Because it's just, they always, they know what they want you to say, and they'll ask the question 15 different ways until you give them the answer that they want. So, anyway, other questions, anybody?
Let me give one more here.
Well, very unscientific question. I had trouble following a fair amount of what you were talking about. But just looking at it as a layman, is there a chance, what is the length of time that could be envisaged before, let's say, the Gulf waters return to the states and flow, if at all? Is there a possibility, like half-life of an isotope or something you look at that might describe?
Well, I can tell you, I can give you 2 examples. Exxon Valdez still is not, the Prince William Sound is still not the same. The herring fishery never recovered. The salmon fishery is not the same. There's still oil in places, under rocks, under crevices here and there. So, decades. The Hitchcock blowout in the Gulf of Mexico in 1979 was the closest thing to the Deepwater Horizon blowout. That was only in 75 meters of water, but they used dispersers. They used essentially Crest at 9,500. And the coral communities off the coast of Mexico around Veracruz, where that stuff came ashore, died and have never come back. So that was 1979. So I think that I don't think we've even seen the ecosystem, like fisheries level effects yet, because those take years to propagate through the system. I think we'll start to see those in the next 2 to 3 years. And in terms of recovery, I've not seen a flying fish, for example, on a cruise since the oil spill. And you used to see flying fish all the time. And they're just, maybe they're not where we are, but they're just not abundant. So I think these deep water corals, a deep water coral that is 1 meter high is 500 years old. And many of these organisms were completely decimated and killed. So 500 years to rebuild that coral, So I think it depends on what you're talking about, what part of the ecosystem. I think some parts of the ecosystem will recover in a decade or so, and other parts of the ecosystem will recover in 500 years. So it's really, it's hard to say. And the crazy part of it is that we're never going to know the answer to that question unless we continue monitoring. And the money that's paying for the monitoring right now is the $500 million that BP donated to the Gulf of Mexico Research Alliance. And good on them for doing that. That was a good thing to do. But that's going to fund about 10 years worth of monitoring. And what happens after that? Who covers the monitoring cost after that? The answer right now seems to be nobody. And we're going to need to keep monitoring for a lot longer than 10 years to figure out what happened. And it's not just monitoring, but it's better understanding the natural seeps. Because we still don't know. I mean, we've been doing a lot of work at natural seeps as part of our GOM-refunded project. It's called Ecosystem Impacts of both oil and gas in the Gulf. And through EcoGate, we're working at mechano-impacted sites and we're working at natural seeps. And what we're finding is that there's so much spatial and temporal variability at these natural seeps that it's just hard to wrap your head around. You go over here and you get one thing, and you go over there and you get something else. And every little seep is distinct and different. So how do you characterize the background baseline of a system that's so incredibly heterogeneous? And then the other part of that is the water's moving all around. And the distoceanography of the Gulf of Mexico, the models are all over the place. Joe's model tells you this, Fred's model tells you that, Sarah's model tells you it goes over there. So there's a lot of work to be done to figure out where the water's going, because if there's an oil spill off Cuba, the Chinese own most of the drilling rights off Cuba, so 90 miles from Florida, if there's an oil spill, a blowout off Cuba, who determines what the response is? There's no international treaty. There's no treaty between us and China. I mean, it's kind of, the only international oil treaty in terms of response is the North Sea Alliance Treaty. And all the North Sea states have signed on to a treaty that says if there is a blowout or an oil spill or a gas well blowout, etc., we will all respond in the following ways, and we will do, everybody's going to help, everybody's going to pitch in, it's going to be a team effort, a team response. In the North Sea, you can't produce a well until you drill a relief well. So they've already got the relief wells in place, so all I have to do is go in sideways and plug the hole. It would take maybe 3 days. That's a really smart thing to do, but it would cost an extra, probably $20 million. But these are companies that make profits of $40 billion a year. So what's $20 million? I mean, to me, it's just, there's no excuse for not taking the extra precaution. Because, BP basically thought they were going to save $12 million by plugging this well a day early. And it's going to end up costing them, I bet you, $100 billion in fines and penalties and whatnot. So $6 million, $100 billion.
Many thanks for coming with us tonight. It's a fascinating story. I'm sure and let me welcome you back to the next Cherry Friday night, November 1, our own Stuart Pickett, staff member here at Cherry Institute. We'll talk on the ecology of cities in crisis, and what to expect when we look at a city as an ecological system. And of course, as always, these kinds of programs are brought to you by the generosity of donors to the Carey Institute. It's going you're feeling like you've enjoyed the programs and want to help, we'd be glad to talk to you. But many thanks for coming tonight.